Welcome to The Explainer. Today, we're going to tackle a huge topic. How does a neural network actually learn? And we're going to build it all from the ground up, right from scratch.
All right, so how does a machine actually learn? It's not some kind of magic. At its core, it's really just a mathematical process of trying to minimize its mistakes, one tiny, tiny step at a time. And to really wrap our heads around it, we have to start small.
I mean, really small. We're going to build this thing from the ground up, literally. Because before you can even think about a massive network with millions of these things, you got to master the mechanics of just one single neuron.
Okay, so let's jump into our first section. We'll start right there and see how the very first idea of an artificial neuron, the perceptron, had to evolve into something a lot more powerful.
The original perceptron neuron it's beautifully simple. First, you've got this step called pre-activation, where it just adds up all its inputs, each with its own little weight. Super simple. Then the activation step makes a hard call. If that sum is positive, bam, it fires a 1. If not, it fires a 0. It's basically just a digital on-off switch. And this right here, this is the perceptron's fatal flaw. That hard on-off switch, that red step function you see, it isn't smooth. It's got these sharp corners, which means it doesn't have a useful gradient. And you can just think of a gradient as a slope. It tells you which way is downhill. Without that slope, our main tool for learning, gradient descent, is completely lost. It has no idea which way to go. So we need something that changes smoothly, something like that blue S-curve, the sigmoid function, to give us a little nudge in the right direction.
And that brings us to the absolute heart of this whole thing. We've got our neuron, we've given it a nice, smooth activation function, so how do we actually teach it? How do we tell it which way to adjust its little knobs, its weights, to get a better answer next time?
Well, at its core, learning is really just this. It's a step-by-step process of taking little steps downhill, always trying to find the bottom of the error valley. At each step, we take our old weight and we just nudge it a little bit. And we nudge it in the opposite direction of that error gradient. So the entire secret to learning, the whole magic trick, is figuring out that last piece of the formula. How much does a tiny, tiny change in this one weight affect the final error?
Yeah, this is the whole game, right here. If we can calculate exactly how much a tiny little tweak to one single weight, maybe one that's buried deep inside the network, affects that final error, well then we know exactly how to adjust it. All the magic of machine learning boils down to solving this one little calculus problem.
So how do we do it? Well, here's the really clever trick we use, the chain rule from calculus. See, we don't have a direct line from the weight all the way to the final error or loss, but as you can see here, we can trace a path of dependencies. But we have to go backward. The final loss is affected by the prediction, okay? The prediction is affected by the pre-activation, right? And the pre-activation is affected by the weight. The chain rule is what lets us just multiply the influence from each of those steps together to get the final answer. It's like a game of telephone, but for derivatives.
All right, so let's scale this up. Let's move to a full network and see how this all comes together. Because that simple chain rule logic we just saw for one neuron, that's the seed for the entire backpropagation algorithm, the thing that powers pretty much all of modern deep learning.
Now, if you look at a weight that's connected directly to the output, let's say W3 right here, the path is super short and sweet. It looks almost exactly like the single neuron example we just did. The loss is influenced by the prediction, which is influenced by the pre-activation, which is directly influenced by this weight. Easy enough.
But check out what happens for a weight that's buried deeper in the network, something like W11. Suddenly, the path gets a lot longer. We have to trace that error signal all the way back from the final loss, through the output neuron, then back through the hidden neuron's activation, and then its pre-activation before we finally get to the weight we want to update. This right here is backpropagating. We are literally propagating the error signal backward through the layers of the network. That's where the name comes from.
And as you start tracing more and more of these paths, you realize there's a simple recipe to it. You can almost think of it like you're passing little messages backward through the network. And the message you're sending is basically a product of three things. The strength of the connections you travel along, that's the weights. How sensitive each neuron is that you pass through, that's the derivative of the activation function. And finally, what the original input was that kicked this whole thing off way at the beginning.
Okay, so let's put what we've learned about network structure to the test. We're going to tackle a classic exam question. I'm serious, this comes up all the time. You get shown a diagram and asked, how many trainable parameters are in this network? It sounds simple, right? But there is a very common trap.
Now, for a standard, fully connected network, that means every neuron in one layer is connected to every neuron in the next, the math is pretty straightforward. For the weights, you just multiply the number of neurons in the layers next to each other. So 3 times 4 plus 4 times 4 plus 4 times 1. For the biases, you just add 1 for every neuron that's not in the input layer. So 4 plus 4 plus 1. You add all that up, and for this 3-4-4-1 network, you get a total of 41 parameters to train.
But what about a network that looks like this? The number one mistake people make is they just apply that formula without thinking, assuming every network is fully connected. But look closely at the diagram. The connections, they aren't all there. This is the trap.
So the key takeaway here is super simple. You have to count what you actually see. You can't just go on autopilot and apply the formula. For this network, if you actually count the connections one by one, you get 15 weights. Then you add the 6 biases, and the answer is 21. A totally different number than what the formula would have told you. So please remember, always check the diagram.
All right, to wrap things up, let's do a quick review of the toolbox we've been talking about, the activation functions. These are the nonlinear workhorses that really give neural networks all their power, and picking the right one is a huge part of the job.
So we've already met the sigmoid function, right? It's famous for taking any real number and just squishing it down into a range between 0 and 1. This makes it absolutely perfect for the output layer when you're doing binary classification, because you need something that looks like a probability.
Next up is ReLU, or Rectified Linear Unit. This is, without a doubt, the most popular activation function for hidden layers today. And its definition is just incredibly simple. If an input is positive, it just passes it right through. If it's negative, it turns it into a 0. That's it. And that simplicity makes it super fast to compute. Then you've got tan, or hyperbolic tangent. You can think of it as sigmoid's cousin. It's got that same kind of S shape, but instead of squishing the output between 0 and 1, it goes from -1 to 1. The big advantage here is that it's centered around 0, and sometimes that can actually help networks learn a bit faster.
And really, that's the main takeaway for this part. There is no single best activation function that works for everything. The choice is a critical part of designing your network. You might use ReLU for all your hidden layers, and then slap a sigmoid on the very last layer for your output. It all just depends on the specific problem you're trying to solve.
So think about the journey we just took. We went from one single neuron to the chain rule, all the way to a full network that can learn using backpropagation. We went from a simple on-off switch to a complex learning machine. And that leaves us with a pretty profound idea, doesn't it? That all the incredible, almost magical intelligence we're seeing in modern AI, it's really just the result of this one simple process, repeated millions of times over. Millions of little units all making tiny local corrections, working together. It really makes you wonder, what else could emerge from such simple rules?